I mean, probably. Yes. Fancy chicken. Or not chicken. No, this week isn't that one. So we got 9.
So I put in the test 2 grades. Do you see your grades? You guys look. So again, I've got another one of these charts. Between this line and the line up here is the A's, and the blue dot tells you the raw score, and the orange dot tells you what, after the makeup points, you could possibly get. So the A's up here, the B's in between these 2 lines, the C's in between these 2 lines. There are a couple of very low ones, and these dots here represent how far up you can get. After the quizzes that add points to test 1 and test 2, if you're still in a low range, just realize there's still 2 more grades to go. Also, realize I am going to calculate your grade 2 different ways, your overall grade. One with the final being 25%, and one with the final being less. That way, if you've been stuck in that low range and you do really well on the final, I'll calculate it the way that I'll calculate everybody's grade 2 different ways, and whichever way is best, I'll keep that for you. So the 2 different ways to calculate your grade isn't going to hurt you one way or the other. But I just think the final is probably just going to be harder because it's cumulative. So you might want to break on that. But then again, you might want the final to count a lot. So if you're in that low range and you're worried, you should meet with me some before test 3 to make sure you do really well on it. I mean, those grades, even if you're in this low range on the first 2 tests, you're at least in range of a C. Nobody's outside of the range of a C. So focus on test 3 that we're about to start, info for test 3. And maybe meet with me to study for the final 2. But just try not to despair. I've been stuck there as a student of many years. As far as those makeup points quizzes, I think I've decided I'm just going to do those. I'm going to make a special bank of them on D2L and those quizzes, so you do them at home, so you have time. I might even let you take them unlimited amount of times. So it's just up to you to maximize the amount of points that you get added to your quiz. I want to do that just because of class time. I want to use up the class time doing the quizzes. And that'll make it easier for you, so that if you're stuck in one of those low ranges, realize there's still hope. I could make some homework questions, but I would do that in lieu of, instead of, the makeup points, and I think the makeup points is the best way to do it. All right, so that's the test. Oh, I have these 2 students who were sick for the test. And one of them I know went into the hospital or something, and I haven't heard back from her. The other one was going to take it this afternoon, but I just got an excuse from her too, so I don't know what's going on with them. So I can't hand out the test and go over the test and all of that until they've taken it. So it might be early next week before we can actually go over it. And again, in interest of class time, I'm probably just going to post the answers on D2L so you can check your test against it. I want to do that at least, just in case I've made a mistake in grading. That's why I always go over it. Y'all know I make a mistake or 2 on my tests. I make a mistake grading sometimes too, so it'll give you guys a chance to double check my grading. So I will post it at least, but I don't know if I want to spend class time on it. So, but you could always come to me and ask me. Once I post the answer key, you can come ask me about things. All right, in terms of what we have left to go over, we did chapter 1, 2, 3 for test 1, 4, 5, 6 for test 2, and we're trying to get through 7, 8, 9 for test 3, but I have to pick it back up in chapter 6. I just wasn't gonna try to get through all of this before time for test 2. And this is where we are, reaction rates. Keep an eye on the video, y'all. I'm gonna keep it visible. Just because we're starting fresh with this. I guess that'll work. All right, so starting information for test 3. So we talked a lot about energy in reactions. We had those energy diagrams. The rest of this chapter is about, well, still about energy in reactions. So in this blue box here, in section 6.4a, it says increasing the concentration of reactants increases the number of collisions, so the reaction rate increases. So there's 2 reasons why. So picture this, you've got, let's just say that you've got a big beaker of water and you've got 2 reactants in there and they need to react to become the 2 products. You can look down here if you want something to look at when I discuss this. These are gases. So actually let's picture this, let's picture a big beaker. Got a big beaker and it's sealed and those gases are in there. Let's say I put the O3 and NO in there and seal it up. And it's at a certain temperature. All right, let's just say room temperature. These molecules have to float around in there and they move at a certain speed and they collide with each other at a certain rate based on the speed. And they can't react unless they collide with each other. So they have to at least bump into each other. And then some bonds break, things reconfigure, and new bonds form to form these, and then those float out into the reaction chamber. So one by one, they bump into each other and start making these. But they have to bump into each other for that to happen. Temperature is literally, raising the temperature literally means they're moving faster. And if they're moving faster, they're going to bump into each other more often, collisions. But there's 2 reasons why that increases the rate. One of them is it takes some energy to break the bonds, and it's using that collision energy, literally the mechanical energy of banging into each other to help it break the bonds. So they have to bump into each other with enough energy to break those bonds so the new bonds can form. And temperature is really not every molecule in there, not every molecule is moving at the same speed. Their average speed is really what's increasing. So there's a sort of a bell curve. And then if you increase the temperature, that bell curve shifts up a little. So what I'm getting at is they can bump into each other, but they just happen to be going on the slower end of speed. They won't react every time they bang into each other. But if you increase the average temperature, then more often when they bang into each other, they will react. So it's 2 reasons. It's the amount of kinetic energy they have is higher when you raise the temperature, and the collisions are more frequent. However many collisions per second increases. So there's 2 reasons why increasing the temperature increases the reaction rate of the reaction. And vice versa for these. You decrease the temperature for the same reason. Less energy in the collisions and less collisions per second, collision rate. So that's the reason playing with temperature can affect the rate, literally because of collision. I think for these sections, I'm going to go through, actually go through all these practice problems. Oh yeah, so for the same thing goes, so 2 reasons why raising the temperature increases the reaction rate. And also, almost for the same reason, increasing concentration of reactants. Meaning, and it really is just one of them. If I put if I've got that reaction chamber and I run the reactor and the time, how long it takes to make all of this. And then I set up that same reaction chamber, same amount of stuff, except I put a little more O3 in there than I did before. Same reason, there's more collisions per second because there's literally more of these to do the colliding. You see what I'm saying? Put a little more in there, then there's gonna be more collisions. I could put a little more of that in there, there'd be a little more collisions, just because of the odds of running into something. Does that make sense? So, increasing the concentration increases this reaction rate. Increasing the temperature increases the reaction rate. And vice versa, decreasing concentrations will decrease the reaction rate. And decreasing the temperature will decrease the reaction rate. And literally based on what I just said, you can answer this question. Here's your reaction. What effect would these things have? If you increase the concentration of O3, O3 is right there. So increasing the concentration of a reactant, O3, increase the rate. Decreasing the concentration of that other reactant, NO, will decrease the rate. Increasing the temperature will increase the rate. Decreasing the temperature will decrease the rate. Makes sense, right? Okay. A lot of this that we're going over here is all just conceptual. There's not really calculations to go with it. So today, probably this week, it will all be like that. Okay, here's another way to increase the reaction rate. A catalyst. I'm going to do this energy diagram and I'll just make up. So you've got reactants, you've got products, you still have this. You remember what this is called? Symbolized E with a little a.
Activation.
Activation energy. Increasing and decreasing the temperature and increasing or decreasing concentrations doesn't do anything to the reaction rate, but a catalyst literally does this. If I do this reaction without a catalyst, that's its reaction profile. If I use a catalyst, it just decreases the amount of energy needed to make the reaction occur. Other hallmarks of catalysts is the catalyst remains unchanged. It might undergo some changes, but by the time you get all the products, you just get the catalyst in its same form back. So a catalyst is another way to increase reaction rate. They give examples of some catalysts. So here the PD is the catalyst, this is palladium. Literally this reaction, you don't need to really know this, but just to get an idea of how this works. If you have a metal surface, so you literally put a chunk or flakes of palladium in the reaction, like if it was in a liquid form. This will be done as a gas though, so I think you just run these two things as a gas through a palladium, forgot what you call it, but think of a disc of palladium with lots of little holes in it, and you're running these gases through there. Hydrogen, the H2, it's sitting there with one bond, so these are the H's and here's the bond. When it sits on that palladium surface, it sort of weakens the bond a little bit. So you have to put energy in to break bonds, but you can mechanically sort of pull them apart a little bit. So when they sit on the surface of the palladium, it messes with the electrons in that bond and they kind of weaken. And then when the ethylene comes along, that's already weakened, and those two hydrogens can more easily add than they otherwise would. So it's kind of a mechanical thing. And another example of a catalyst, this is literally what a catalyst does. It's showing you the lower activation energy. Enzymes, you'll study these next semester, take 1152. These act by, now these are huge molecules. This is a huge protein. There's thousands of atoms in it. And here's lactose, this is two different molecules with a bond in between them. You'll study those two disaccharides. And enzymes are the way your body catalyzes things. And this pocket, completely different from the way, not completely different, but it's still kind of a mechanical thing. But you got this huge molecule, what we call the active site, this little pocket. It fits perfectly in there. And proteins tend to like move a little bit. They're just sitting there, they just kind of fluctuate a little bit. And as it moves apart, it'll actually either pull that bond apart or weaken it a lot, so it's very easy for the reaction to take place. And then it breaks it off and it makes it two separate molecules. That's how an enzyme works as a catalyst, decreasing the activation energy. That shows the result there. There's something on catalytic converters here, and how you deal with car exhaust, but I won't go into it. All right. So I guess I could summarize. Increase the reaction rate by increased temperature, increase the concentration of the reactants, and a catalyst. And these two, the first two, vice versa. Decrease the temperature, decrease the reaction rate, decrease the concentration of reactants, decrease. I guess you could say increase the amount of catalyst or decrease the amount of catalyst. But usually it's more like you use a catalyst or you don't. And putting your catalyst in will speed things up. So that's a straightforward enough little set of ideas. But reaction rate, next we're going to talk about equilibrium. And there is a thing about rates in equilibrium discussion, but I'm just saying we're kind of shifting gears here. So this is doing something fairly different than you guys have seen before. You see this double arrow? That tells you that every other reaction I've shown you, like these up here, back up to this one, there's a single arrow, and that indicates, we say, the reaction goes to completion. Meaning, the reactants, a little time goes by, they bump into each other, and everything in there in the reaction vessel becomes products. That is, goes to completion, and there's no reactants left over. There are a lot of reactions where it only partially goes to completion, and when it stops, when the reaction stops, there's still a little bit of reactant there and some product there. They just both coexist in whatever reaction chamber you've got. Like this was gases. Let's go down here. I think these were gases too. Yeah, these are all gas. So these would be in a little sealed up chamber. But if you put CO2 and H2O together in a reaction chamber, you do get some monoxide, that's CO, not CO2, and H2O. Some of it will react and become these things, CO2 and H2, but some of it will remain. And basically what happens is if you just put those two reactants in, sealed it up, and let it sit, over time, some reactants become products, a little more reactants become products, a little more reactants become products, and then at some point it just stops. And you're left with some of the reactants still there with some products also there. So when you have a double arrow like that, it means all four of those things are in the reaction chamber after it stops reacting. Oh yeah, okay, so we call those reversible reactants. And it's probably worth pointing out, once we start talking about equilibrium like this, if I write it down like this, you call these the reactants and these the products. But you see that this is, what is a reactant and what is a product is kind of arbitrary now. Because I could write this down, I could write those two things down, not write that. Write those two down, put a double arrow here, and put those two things here, and it's still a perfectly valid expression for what's going on. Meaning if I put these two and these two alone in the reaction chamber, they're gonna react and make some of this, and they'll just keep going and make some of this until a little bit later, there'll still be some of this and some of this. So saying which one is the reactant and which one is the product is a little bit arbitrary now. But by convention, if I happen to write it like this, then I still call these the reactants and these the products. I'll just use those words to refer to what's on the left and what's on the right. But it is a little arbitrary calling one reactant and one product. And they're kind of making a big deal about forward reaction and reverse reaction. If I wanted to write down what is the forward reaction for this, I would write what you see there. I'm not going to put the G, CO plus H2O yields CO2 plus H2. That's the forward reaction. If I wanted to write down the reverse reaction, I would just reverse it. I would go CO2 plus H2 yields CO plus H2O. As that's written, that's the forward reaction, that's the backward reaction. So don't overthink that. What's the forward reaction? What's the backward reaction? Or the reverse reaction? All right. I'm explaining what's in the blue box here. Let me take it back up a level. This can feel a little complicated, but you've got reactants. If I had a reaction chamber and I put nothing but reactants in it, what happens is over time, some reactants become products, reactants become products, a little more, and that reaches a certain ratio of. These brackets mean concentration. Write it down here. You put the products on top, the reactants on bottom. K means concentration, but we haven't really talked about that yet. That doesn't come up until the next chapter in this book. But that would be like grams per liter. We usually do things in moles per liter. But I know the brackets look weird, but it basically means an amount of products and the amount of reactants. So reactants become products, and then at a certain ratio of reactants to products, amount of reactants and amount of products, it stops and it will just stay there forever. And whatever this comes out to be, if you calculated it, that's called the equilibrium constant. That's the equilibrium constant, K. And the whole point of having the equilibrium constant, or talking about the equilibrium constant, is this. If I put only reactants in that reaction chamber, over time the reactants will become products, until the ratio of their amounts equals some constant. That's why it's called a constant. But notice also, if I put nothing but these into the reaction chamber, products will become reactants, a little more, that'll go until you reach that same ratio, and then it'll stay like that forever. So there's a little bit of time, sometimes it's like instant, sometimes it could be years. The amount of time it takes for iron to rust takes a long time, but it's still in equilibrium. And you could also put some random amount of reactants and some random amount of products into that reaction chamber, and whichever way they need to react, like increase this while decreasing this, or increasing this while decreasing this, whichever way they have to go, they will go that way and react however they have to until this is back to that constant. So this particular state, when there's a certain amount of products and a certain amount of reactants, that's a particular constant for every reaction there is. So it doesn't matter how much of the reactants and products you put in there to begin with, they're gonna do what they need to do to end up in this state. You see that? So that opens up a handful of fun concepts, depending on if you're thinking. It is warm here, right? I'm not crazy. All right. So what this is saying about rate, I might be able to get away with not really talking about it. But if let's say that this constant is, for this particular reaction, let's say it needs to be 150, whatever it comes out, 150. So if this number is smaller than this number, then you'll have a number greater than 1. If this number is bigger than this one, you'll have a number less than 1. Do you see that? Everybody understand that? Like if you had, that's less than 1. This number big, this number small. But if you had, that's going to be greater than. So equilibrium constants can be greater than 1, sometimes way greater than 1. Sometimes they can be less than 1, sometimes way less than 1. So if this was supposed to be 150, and you started out like that, like I put a bunch of reactants in it, and let's say, let's not be that specific. Let's just say the concentration turns out to be 1,234. It's not at equilibrium, but what happens is a little bit of reactants become products, a little bit of reactants become products. So the next time frame, a minute goes by, and let's say you've got 2 there, and 1, 2, 3, 2. So this has gone down a little bit while this goes up a little bit. See what I'm saying? A little more time goes by. Let's say we're at 10 and 20. So now we've lost 10 units from down here, came up here. Reactants becoming products. That's going to go on until you have a large amount of products and a small amount of reactants, whatever that has to be, to hit that constant. So if you put nothing but reactants in there, a little time goes by, it ends up hitting that equilibrium, and you'll have this ratio such that you'll have 150 for your constant. What's happening there is, remember I said rates depend on concentration? The more reactants you put in there, the faster this arrow will go. And when there's 0 products here, where we started, this rate is 0, but this rate is very high. So let me do this. This is a number line, and let's say that's 150, that's 100, 50, 0, and then down here we have -50, and so on. Right, and basically here you're starting at 0. You would have a K of 0, but the K is, you don't really call that the equilibrium constant until you get to equilibrium. This rate starts out at 0, and here the rate's starting to increase. Yeah. So the reactants becoming products starts out at some kind of low number. No, it's some kind of very high rate. Yeah. That upper rate
or at some very high rate. But as reactants start to become products, the concentration of the reactants are going down. They're going down. And as a little more time goes by, they'll go down some more. But as soon as there's some products, a tiny amount of them, the rate going this way goes from 0 to something a little higher than 0. So here's the products becoming reactants going up. So that continues for a little while until they meet somewhere. And once they meet somewhere, the reaction stops. See what I'm saying? This rate, if it's nothing but reactants in there, this rate starts out really fast. And then as soon as there's a little bit of products, this starts going slow. But this one is slowing down while this one is speeding up. So this one's speeding up, this one's slowing down. And when they get to the point where they're going the rate the same way, there's no net change in products and reactants, and they stay in those amounts forever. They are reacting, but they're reacting at the same rate at a certain proportion. Make sense? That complicated bit doesn't come up too much in your thinking, but I thought it was worth going through. So it's not really that the reaction stops, it's that the forward and backward reaction are going at the same rate, and at whatever concentrations they were at, they stay at that concentration. Make sense? There's just as much products being created as products being removed and becoming reactants any given moment. So this net change is 0 with them. When I said don't overthink that, identify the forward and reverse reaction. Well, what you're looking at is 3 forward reaction as is. If you remove one of those arrows and you just leave the arrow going to the right, there's all your forward reactions. And you just have to write it around the other way to show the reverse reaction. So I've introduced the equilibrium constant. I won't have you calculate equilibrium constants, really, because that's just an exercise in mathematics. There's really not much to do with it. When we get to concentrations, what I have in the bracket here, concentration of C, they even usually have a power of 10. And your intuition's not going to grasp this. You have to take a thermodynamics or kinetics course to see why this would be the way we would express K. But this is how you do it. You have the coefficients. Reaction here? Yeah, so here's a reaction. That's that coefficient that you use to balance the reaction. You put that as a superscript. So for the whatever the concentration of C is in the reaction vessel at equilibrium, and whatever the coefficient is, you put it there. So if it was a 2, this would be like the numerical value for the concentration of C squared. And then you take the concentration of D and whatever this is, you put that there, you calculate that, you multiply them together. That's really what I have as this is more literally true. This is the way I tell you guys to think. Because if you increase the concentration of the products, or just even if you increase whatever numerical value you have for C, this number is going to go up. Whatever you calculate for the numerator is going to go up. And if you decrease one of these concentrations, whatever you have in the numerator is going to go down. So you really don't have to think like this. Explaining why it would be like this with those coefficients being the superscripts, the powers, your intuition isn't ever going to see into it. But I would give you this, and this on the test. But this will show up in the logic we'll use for some of the questions. I might have you do this. Write down the expression for the equilibrium constant. This is actually very easy. You're just following that pattern up there. Yeah, I guess you can see it. But I'm just following, this. That's a 3. I think I can move this the way I want. So what that question is asking for is K equals, I do the products on the top. So it's just this CO2, whatever the concentration of CO2 is, and then that 2 that I'm squaring it with is this 2. And then on the bottom, I have 2 reactants, CO and O2. CO has a 2 on it there. If you actually had to cut the concentrations in hand, you could calculate that. It would just be a pain in the butt. But I won't have you calculate those. But that's the answer to this one. So don't overthink those questions either. And you could do these two. If I had a reaction vessel, I'll keep this here. K equals the amount of products over the amount of, just think like that to answer these questions. And I've got some reaction. I'll just say, all right, the value of K, you can still qualitatively know a few things just looking at the value of K. Colors. A situation where K is, let's say, K is way, way, way bigger than 1. And these usually come with a power of 10. They're not showing an example there, but let's say K equals sometimes they're huge. This situation is telling you that there's way more product than there is reactant. A huge K tells you there's way more product than reactant. It's probably too big. If I drew that, let's say this is my reaction chamber. And it doesn't, like I said before, it doesn't matter how much reactant product I put in there at the beginning. It's going to react in such a way as to have lots of product in there. Lots of product in some little amount. There, that might be a good representation of a K of 6.3 times 10 to the 20. Because there's a very small amount of reactant and lots of product. And you can analyze all the situations. It's probably too big of a number to use here, but they're still usually huge. I know you probably already wrote it down in your notes. But let's just say that it's 10 to the 9. All right. The situation where K is way, way, way less than 1, and that would be a K of, say, 2.4 times 10 to the negative 7. It would be just the opposite. I could go about changing my dots, but it'd be easier if I just did this. There. Now I don't have to redraw my dots. So now it's mostly green with a few dots of product. That's the situation when this is very, very small.
Does that make sense? And you can get that logic thinking like this. Products over reactants. At equilibrium, you have mostly products when this number is huge. And at equilibrium, when this number is very small, you have mostly reactants. Follow this? So qualitatively thinking about what K value tells you. And of course, what do you think you would get for a K value if it's about 50-50? About half reactant, half product at equilibrium. What? It would be very close to 1. If it's exactly 50-50, same amount of product and reactants, this will literally be 1. But somewhere close to 1, you assume it's about half and half, qualitatively. You follow that? So that's what this little section is, explaining that you can know a little bit about what the equilibrium is just by looking at the value of K. And this is just a summarization of that, table 6.4. I don't use these pictorial diagrams, but maybe that helps you a little. This last little blue bit here, this is a little wishy-washy. It's just true that most of the time this is true, but it's not always strictly true. That reaction diagram versus that one. Do you remember what this is? This difference between the reactants and product. Delta H. So that's the delta H. This is a negative delta H. And this is positive delta H. Positive. It tends to be, these still have a delta H, these reversible reactions still have a delta H associated with them. But when it's a negative delta H, most of the time the equilibrium is shifted towards the product. Meaning a very high delta H is negative. Usually that means K is very large number greater than 1. And the opposite here when delta H usually K equals. But it's not always true, so I'm kind of surprised the textbook says that. They do say it in a wishy-washy way. There is, however, no relationship between K and the reaction rate. Let me save that. But products of a reaction are favored. The products are products are favored when K is much greater than 1 and H is negative. K much greater than 1 and vice versa. So another little set of bits of logic there. All right, so look at this problem. Problem 6.7. Given each equilibrium constant, state whether the reactants are favored or the products are favored. Favored just means more off. Favored is kind of a wishy-washy way to say it, but many textbooks use that. I'll also say shifted to the right or shifted to the left instead of products are favored is the same phrase as me saying shifts to the right and Reactants being favored, I will sometimes say the equilibrium is shifted to the left. But if you just look at these values, I guess that's a 10 to the negative 4. So this is a very small value. Is it reactants or products? Come on, y'all play along. It's a very small K value. Are you taking notes? Lots, yeah, reactants. And then very large number, the products are favored. I wouldn't call 350 a large number, because these are usually very, very large or very, very small numbers. But this would be kind of close to 50-50, but still favoring products, the 350. The 0.35, that's less than 1, so that's going to favor reactants just by a little bit. You following this logic? For all these types of questions, you've got to use this logic. There's no math to do. So you guys following me? Calculating equilibrium constant, don't worry about calculating it, but it's the same thing that was up above there. This is how you would set it up. This is actually giving concentrations. The M means molarity. I'm kind of sidestepping this because this book doesn't do molarity until the next chapter. But you could calculate it. It's just a messy math problem to do. And this is another one, calculate. I'll calculate these though. Le Chatelet's principle. There's 3 things to discuss with Le Chatelet. It's pronounced Le Chatelet. I guess I'll use that reaction. 2CO, that's a gas, plus O2, double arrow tells you that it's reversible. I always do this with kind of a pantomime to help you remember it. So let's say this is sitting there at equilibrium in a little gas chamber, and I've got a little nozzle, and I can pump in a little bit of O2. So I can increase the amount of O2. Earlier when I was talking about increase this, it'll increase the reaction rate. There was a single arrow here, and we were talking about these that go to completion. Realize I'm not talking about reaction rate now. I'm talking about the K value. But if these are the reactants, and that's the products, and it's the amount of reactants so I increase the, I did that backwards. I didn't make that mistake before, did I? Reactants always go on bottom, product is always on top. Did I make that mistake earlier? All right, well, let me say it one more time to be sure. Product always goes on top. Reactant always goes on top. So if I increase the amount of reactants a little bit, this will increase a little bit, and then over time, I mean, between the time it was just sitting there and the time I crank that in, a little time goes by, and now K will be a little bit smaller because I've increased the denominator a little bit. And then a little time will go by, and some of the reactants will become products to equal it out. I add some O2, we actually have the K will decrease a little, but then over a little more time, K will increase a little more, and then K will increase a little more, and K will increase a little more until it comes all the way back to this K. Meaning, I increase the denominator a little bit, and that makes K go up, but then some reactant becomes product and goes down a little more, reactant becomes product, goes down a little more, until it gets back to what that original K was. And that's not about the rate, it's just about this shifting to get back to that ratio that it likes to be in. So the simple way to say it is, I add some O2, it shifts to the right. That's the quick, simple way to do it. This is my pantomime. Add some of this, it shifts away from there to the right. Vice versa, if I remove some of this, it shifts to the left. When I say shifts to the left, when I remove this, it changes the value of K, and then it shifts to the left to correct its way back towards the K that it wants to be in. If I add some of this, it shifts to the left. If I add some of this, it makes K go down, and then it shifts to the left a little more, a little more, a little more, until it gets back to that K. If I remove some, it shifts this way. If I remove some, I suddenly made K go up, but it shifts this way a little more, until it gets back to the K. So remove this, we shift this way towards it. I add this, we shift this way away from it. But it doesn't change K. K stays the same. It might, the answer to this calculation might change a little bit, but it changes back and becomes the K, the original K that it was. So Le Chatelet's principle says if you add some reactants, it shifts towards products. Except the longer way to say it is, over time, it shifts towards products in an effort to get back to its original K value. Follow that? So add some of this, shift that way. Add some of this, shift that way. Remove some of this, shift this way. Remove some of this, shift this way. And the same here, if I add some of this, it shifts that way. If I remove some of this, it shifts this way. So whatever I add, you shift away from it. If I add to reactants, you shift away from reactants. If I add products, you shift away from products, and vice versa. That's Le Chatelet's principle. You follow that? And notice K doesn't change. I want to emphasize that, because the next two things I'll show you actually changes K. All right, shift to the left, shift to the right. Concentration changes is what I was just talking about. Changing the concentration. If I'm adding to it, I'm increasing the concentration. If I'm removing from it, I'm decreasing the concentration. That's it. What I just described is what all this is describing. So for this reaction, if I increase the amount of SO2, there's the SO2. The answer is increasing the concentration of SO2, a reactant, drives the equilibrium from to the right to form more product. You do end up with more product, but you also just decrease the amount of reactant, so you're able to get back to the original K. So y'all can look at those. It's basically just a reiteration of what I just said. I want to get to the temperature changes. Okay, the way they phrase this, I'll write it my way. A reaction that absorbs So if I ask you before test 2, products, reactants, and I said, is this endothermic or exothermic? This one's endothermic, because this is the amount of energy in the atoms or molecules at the beginning. Here's the amount of energy at the end. Here's your delta H. That's the delta H. This is when delta H is positive, endothermic. And the other situation is, products, I do that backwards a lot too. Reactants, products. Reactants, products. This is a delta H that's negative. Exothermic, delta H is negative because it's lost heat. Let me do this. This
this is how I tell you to think of this. You have a particular K. Let's see, concentration. When a reaction is exothermic, that means that the amount of energy, the difference between here and here, well, where did that energy go? Well, it left in the form of heat. Releases heat, I guess I should say. Releases. If it's this situation, I tell you to think of it as those molecules aren't the only product of this reaction. Also, heat was a product of this reaction. You see my logic in that? This is my own convention. And when it's this, when heat absorbs heat, that's kind of like heat being one of the reactants. But this is the more intuitive way to think of it. To think of, you make a reaction, heat comes out. The only products of that reaction really weren't just these physical things. It was also the heat that came out of it. Produced some heat. You see what I'm saying? So you can follow that logic to put heat over here. Now you can think in terms of Le Chatelet's principle. If I increase the temperature, like I've got a reaction vessel, it's sitting there, I should have done this. You're going to beat it backwards and forwards. So you've got products and reactants sitting there in the reaction vessel. And then you crank up the temperature, heat it up a bit. That's like adding here. You increase the temperature, you're adding heat, and it shifts this way. All right, but this time, that shift, that's a new equilibrium. All right, let me back up. Reactants and products in a reaction vessel together, sealed up. They come to equilibrium. What I really meant was, whatever the K value is, K values are always, I'll say, K value at room temperature, which is about 20 degrees C. Well, it's defined as 20 degrees C. And which is one. The unit is atmospheres. 1 atmosphere, which is the ambient atmosphere, and 20 degrees C, which is typical room temperature. K values are defined, like if you looked up the K value for some specific reaction, it'll say in the margin somewhere, at 20 degrees in atmospheric pressure, or it might say standard temperature and pressure. This is standard temperature and pressure. So I should have been saying that earlier when I was talking about the K value. It is tied to a specific temperature and pressure. So therefore, if I had a K value, I gotta make something up. It's in scientific notation. And I'll say, at standard temperature and pressure, these 20 degrees in 1 atmosphere. All right. If I have an exothermic reaction, it's already reacted though, it's already given off its heat, and it's just sitting there in a reaction vessel. If I increase the temperature, it has a new K value that you add heat, increase the temperature is like adding heat. You're going to shift towards the reactants. That means the denominator grows a little, and the numerator shrinks a little. That means
see. The new position of the equilibrium is now this, because I've increased the temperature 10 degrees. If it was an endothermic reaction, it's kind of like heat is a needed thing to make the reaction go, just think it's like that. This is the more intuitive one. But now I'm saying, if it's endothermic, add heat on the left side. And now you can think in terms of the Chatelet's principle again. If you increase the temperature, you shift this way towards products. That has the opposite effect. If I increase the temperature for an endothermic one, K will go the other way. So instead of K going down, K will go up a little. And now it's a new K. That's just a new equilibrium constant for 30 degrees C. And vice versa. If it's an endothermic reaction and you remove heat, you shift this way. And the new K value shifts accordingly. Follow that? But in this case, we actually have a new K. It's a higher temperature. You guys follow that? We're almost to the end of this. We'll go over some more problems. One more, and that's the effect of pressure changes. And we only look at the pressure change this one's only useful when you have only gases. It really doesn't have an effect unless there's some gases involved. But in this case, you have to look at the number of moles of everything. I'm going to write, use that equation. H3. All right, and I will write this part. This tells you that it's in the form of a gas, not a liquid, not a solid. All right, and if we just did this in moles, there's one of these and three of these. So you have to think like this. So do you see where I got the 4 from? I've got 1 mole of this and 3 moles of this. That's a total of 4 moles of gas on the left side. Follow me there? And there's only this on this side, so there's 2 moles on this side. And I would tell you, if you're following my convention, put a P over here. The one with the larger number of moles, put a P on that side. And now see if you follow this logic. If I increase the pressure, let's say we're at 1 atmosphere, and then I increase the pressure, then the reaction vessel has all this stuff in there. But in its effort to compress, because I'm pushing on it, it shifts that direction. If I add pressure, increase the pressure, I shift that way. Just, that's its way of compressing into a smaller space. It forces the reaction to go this way. And decreasing the pressure, same way, it'll shift this way. You give it more space to expand into, it'll shift this way and take up that space with more moles of gas. That's it, that's the end of all this logic. We can go over some problems. Guess we don't really have time, but let me go down here. Watch the video. This is about the time it cuts off. But I want to give you a bunch of these to look at. I don't know if we'll have time to go through a lot of them. But I want to go down to reaction rates is where we started. Two reasons why increasing temperature increases the reaction rate. Remember those? Increases the amount of collisions per time, that is the collision rate, and it increases the kinetic energy of the impacts. That's the two reasons. Why does decreasing concentration decrease the rate of a chemical reaction? If you decrease the concentration of reactants, it'll decrease the number of collisions per second.
Does the pressure change, does that also change K, like the temperature does?
Oh, yeah, I should have said that. So changing the temperature, shifting the equilibrium, actually changes the K, and same with pressure. Pressure changes, you get literally a new K at that new temperature. I mean, the new pressure. So I would say, I want to go over these, but I feel so pressed for time, I'm just going to keep looking at the clock. Why does decreasing the concentration, I just did that. Which value, if any, in each pair corresponds to a faster reaction? Remember the catalyst. You got a faster reaction because you were able to decrease the activation energy. Lower activation energy means faster reaction. So if you change the energy of activation from 10 kilocalories to 1 kilocalorie based on putting a catalyst in it, it will go faster. K doesn't affect the rate, so K has nothing to do with it. Delta H has nothing to do with it as well. Back when I said something about a wishy-washy statement, we were talking about equilibrium, that was down here. But the delta H, you can have a delta H of negative kilocalories or plus 2 kilocalories. It can go very slow or it can go very fast. It can be negative 2 kilocalories and go very slow, or it can have negative 2 kilocalories and go very fast. So that has nothing to do with rate. Activation energy for these reactions that go to completion is the only thing you can change to make them go faster. You could also temperature and concentration. The catalyst is what changes the activation energy. But yeah, I guess we'll go over these next class. But I'll go ahead and open this. There's not a lot of questions in here. Let's look at it real quick. So your first quiz available for test 3 is this. When the temperature is increased, the reaction that blank heat is favored. That's going to be absorb or release. I might want to rephrase these a little. That should be a reversible reaction. So maybe I'll tinker with it some. But yeah, you can go ahead and try these, but I'm going to rephrase them a little bit. This book isn't great about phrasing. That, and some of these under these sections we just went over, reaction rates, equilibrium, I would skip the picture ones. Chatelet's principle. I gave you a big hodgepodge of logic today that you're going to use to solve these problems. I think it's best to get a good look at it before we come back Thursday. But I'll review some of this Thursday anyway. You guys okay? This is where we start. Also, if you're in that lower range, your test scores and you're worried, come talk to me. I can make you feel a little better. You should definitely be getting ready for test 3. All right. Camera didn't turn off. We're good.